Hello students, let's proceed with our lectures and I would like to remind you a content of previous lecture when we consider turning on RLC circuit on DC on constant EMF. Before commutation, all currents and currents in all elements and in particular through the inductance was equal to 0 because it was disconnected from the source, and voltage drop across capacitance was equal to 0 also. And we have such initial conditions for t less than 0, and we write down second Kirchhoff's law for this loop for the moment t equal to plus 0. It is here, and from here we obtain equation for derivative of current by time for the first moment after commutation. And by this we determine for the case delta greater than omega 0, we determine equations for current, it is here, and for current, it will be current through inductance and through all elements, and voltage drop across inductance. It is here. You see force will be, you see here, IL force will be equal to 0 because it is steady state DC processes, and all this MI will be applied to capacitor. So UC force will be equal to EMF. We have this equation for current. We can see that at t tends to infinity, I will tend to 0, and we have UC equal to UC force plus UC natural, and it is equation for UC, a sum of forced and natural component, and then we introduce such parameters as T1 and T2. We get this equation for current through these parameters, and we depict this graph for current. It was equal to 0, and it will be equal to 0 at t tends to infinity, and this transient processes a sum of two exponents. One is damping slow, more quickly, more faster, and second damping is more slower, and we have such the graph. And then we would like to, it is necessary to depict graphs of changing in time of voltages. You see, firstly, let's depict changing in time of UR. It will be the same character as I, because UR equal to R multiplied by I. So these two graphs, I mean I and UR, will differ only by this coefficient, and their character will be the same. Then let's depict let's depict UL, and UL equal to L DIL by dt. It's this IL because it's the same current through all elements, and when current increase here, increase for this time, when it increase, UL will be positive. It when it increase, and you can see that it will be in the point when current is maximum UL will be equal to 0, because its maximum level correspond to 0 level of derivative. So it is, you see, at this moment we have UL equal to 0. And when current begin decreasing, therefore its derivative should be negative. and UL will tend to 0 because when IL will tend to 0, you see. So it is graph of UL at the first moment. It will be equal to this EMF because it is necessary for to maintain zero current through this zero current through inductance. It will be equal to EMF, and it will tend, UL will tend to 0 when t tends to infinity. When, one more time, you see, when UR is just similar to I. So when this current is increased, UL its derivative is positive. When it reach maximum, UL will be equal to 0 because it's its derivative, and when IL decrease, UL its derivative will be negative, and it will tend to infinity to 0 when t tends to infinity. And graph you see may be got from equation UR plus UL plus UC equal to this EMF. See, and we can see that as UR tends to 0 when t tends to infinity and UL tends to 0 when t tends to infinity, therefore at when t tends to infinity, UC will tend to this EMF. And it should be complied condition that UC retain its zero value when time equal to 0, you see, and this is UC which can be got UC as UC equal to this EMF minus UR minus UL. It is this graph. If you use this condition UR plus UL with minus, it will be just this graph of UC, and you can see this UC tends to EMF at t tends to infinity. So we have considered this case, and this case is called aperiodic. And aperiodic tension processes, it is such a processes when current does not change sign. You see, current does not change sign. It's all time either positive or negative, but it does not change time. And such aperiodic tension processes occurs when delta is greater than omega 0. And I would like to remind you that delta is r over 2l, omega 0 is 1 over square root from LC, and therefore this condition corresponds to condition r greater than 2 square root from L over C. And this value, 2 twice square root from L over C, is called critical circuit resistance. And aperiodic, it may be concluded that aperiodic tension processes occurs in RLC circuit when resistance of this circuit is greater than this critical level equal to 2 over square root from L over C. I have told you in previous semester that this characteristic value square root from L over C will be used many times later on. So let's consider second case when delta is equal to omega 0. And in such a case, we will have R equal to R critical, and P1 will be equal to P2 and will be equal to minus delta, as was considered in previous lecture. Yes, in such a case, you see, we have it in previous lecture. Yes, you see this first case, and then it was in lecture before. Sorry, it is not in this slides. So when delta equal to omega 0, we have here we have EI equal to I natural, because I forced equal to 0, it will be equal to A1 integration constant plus A2 multiplied by t, and all this multiplied by e minus delta t. Why it is so? Because we have two equal roots of characteristic equation, and therefore solution will consist of two almost equal items, and second item should be multiplied by this t by it means that it's variable t time, so it should be multiplied by this variable. And as I from plus 0 equal to 0, therefore we can conclude that I1 should be equal to 0. And therefore we can write down, because at t equal to 0, we can write down that I here equal to I2 multiplied by t multiplied by e minus delta t. Then let's take derivative from this equation to use second condition for derivative di by dt at t equal to 0 equal to e over L. Let's use this condition and take derivative. When we take derivative from this expression, we will have I2 multiplied by e in the degree. You see, we have product of two functions of time, so it will be equal, derivative from such a function will be equal to derivative from first function multiplied by second function plus derivative of second function multiplied by first function. So we can write down I2 common item, in the minus delta t will be common item also. When we have derivative from this function t, it will be 1. Derivative from this second function will be equal to exponential function, it is before brackets, multiplied by derivative of the argument, it will be minus delta, yes, and it should be multiplied by this first function t. Okay, when we equate this derivative to when we determine this derivative at t equal to 0, and we should equate it to e over L, because at t equal to 0 it should be equal to this value, and at t equal to 0 we will have this item will vanish at t equal to 0, and we will have only this item, and it will be just a2, because this exponential function at t equal to 0 equal to 1, to a unit. So I2 equal to e over L, and we can write down this equation as e over L is I2 multiplied by t multiplied by e to the minus delta t. And from here we can obtain also expression for voltage drop across inductance. It will be L dIL by dt. If we take derivative from this expression, it will be E over L multiplied by L. It will be just E multiplied by and then we have take derivative from product of these two functions, and it will be the same way as here. Yes, it will be 1 minus delta t. Then we can determine UC voltage drop across capacitance. It will be forced component equal to just EMF, because in steady state regime after commutation no current from DC EMF, and all this EMF will be applied to capacitance, so it's forced component. I have taught about it previous and lectures before previous. And then it should be as here we have UR plus UL plus UC equal to this EMF, we can write down that UC equal to this EMF minus UR minus UL. Let's use this expression, and it will be here. You see, it is UC natural equal to UC natural equal to minus RI plus UL, and let's substitute it here. It will be we have R multiplied by I. It is R multiplied by multiplied by R multiplied EMF we put before these brackets, yes. So for the first item it will be just 1, then minus RI, it will be E before, R over L here, multiplied by T, E in the degree minus delta T, in this item here, plus UL. UL, it is EMF before brackets, then in brackets it will be minus E in the degree minus delta T, this item, and minus this minus and this minus will give us plus, and it will be delta T multiplied by in the degree minus delta T. Let's collect like terms. R over L equal to 2 delta minus 2 delta T plus delta T will be minus delta T, it is here, minus before brackets, yes, this EMF, yes, then this EMF multiplied by e to the minus delta T, this delta T is from this item and this item, and from this item it will be minus before, it will be plus 1, and we will have this expression for UC. And this case corresponds to the limiting case of the aperiodic tension processes with the shortest duration. And graphs of voltages and currents are similar to those depicted here, and these aperiodic processes arise with the shortest duration, with minimal duration of tension processes. So, bye for now. Next lecture will be on the topic of oscillation processes, and we will consider it in more details. Bye for now.